We're continuing on here, chapter 12. We were talking about bonding, I believe, and we talked about, again, ionic bonding, which is always between a metal and a non-metal. And because of those periodic trends that we talked about, which is really out of chapter 11, what we really saw was that pretty much metals have trends that want them to sort of release their electrons. They're not going to hang on to their electrons very hardly. And non-metals, on the other hand, have pretty much trends that want to accept electrons. So when these two guys get together, we do get that transfer of electrons from our metal to our non-metal. This is what creates those ions that we talked about, which are cations, which are positively charged, our anions, which are negatively charged. And a reminder that when we have an ionic bond, there's no sharing of electrons. It is that attraction between the positive and negative charge, electrostatic attraction, that holds that together. And that is different than covalent bonding, which is between two nonmetals. And if you look on the periodic table where our nonmetals are, they're the upper right of the periodic table, which means they do share very similar sort of properties in terms of electrons. And basically, they both want to hang on to their electrons, and they really both want to accept electrons. So the best that they could do is have some type of sharing that's happening of electrons. And as we talked about, it could be unequal sharing, which means that you have a polar bond. It could also be equal sharing of those electrons, which means you have a non-polar bond here. And what helps us sort of understand how the electrons will be shared is really the difference in electronegativity values. So that change in electronegativity values, if you remember, when we talk about electronegativity values, it increases as you go up and to the right, fluorine being the most electronegative, and decreases as you come down and to the left on the periodic table. And if we have a difference in electronegativity from 0 to 0.4, that is considered a non-polar bond. And that means basically we have equal sharing of electrons. If it's basically above that, kind of 0.5 to below 2, that's going to be some type of polar bond where we have unequal sharing of electrons. And if it is above 2, but not in all cases, that's going to be ionic. Yes. Thank you. All right, so remember that for the ionic, which is our metal and non-metal, you really don't need the difference in electronegativity values. As soon as you see metal and non-metal, you know you're going to have an ionic bond, so you really don't need it. We really oftentimes will use our difference in electronegativity to help us for our covalent bonding, to help us decide between polar and non-polar. And again, if it's anywhere from 0 to 0.4, we would expect it to be equal sharing of electrons. We could have also, and we could use the general trend in electronegativity a lot of cases without the actual numbers to help us make those decisions, especially if we're comparing somebody in the same row on the periodic table or period on the periodic table. The guy further to the right will be more electronegative, and that usually will result in a polar bond. Also, if you're comparing somebody who's in the same group on the periodic table, the one further up in the group will also be more electronegative, and that usually will result in a polar bond. So in a lot of cases, you can make a pretty good assumption about polarity by just following the general trend in electronegativity, even if you don't have the numbers. There are some places, though, as we saw, that there is sort of a diagonal relationship, like copper and sulfur. They are diagonal of each other on the periodic table. One is further up, one's further to the right. So they sort of cancel out their differences in terms of electronegativity, and they actually end up being the same value. So it is possible to have two different elements that will have the same electronegativity value and will have a non-polar bond and share the electrons equally. Definitely, if you have two that are the same, they will share it equally. Yeah. It's actually on a table, and it would be provided for you, like this table here. And I think you have a similar one in your book, and you basically just look at the table and you can find those values. You don't have to memorize, obviously, those values. They would be provided for you if you needed it. And again, we basically just subtract, the larger number from the smaller number. And really what that tells us is what is referred to as bond polarity. And we're simply deciding between these two atoms how the electrons are really being shared. And that doesn't necessarily translate to molecular polarity, which we'll talk about a little bit later, hopefully. But, it is just really deciding between those two atoms how the electrons are going to be shared. The only place where bond polarity, where we use to change the electronegativity, and molecular polarity, which is the entire molecule as a whole, is really the same, is when we have a diatomic molecule. So if we had something like H2, like we might have talked about, we know that that bond is going to be nonpolar because obviously they have the same electronegativity value. And because that's the only bond in that entire molecule, the molecule will also be nonpolar because of it. And it's just because it only has one bond. Yeah. Cations are positively charged ions as a result of losing electrons. So they become positively charged. They have more protons than electrons. Anions are nonmetals that gain those electrons. So now they have more electrons, negative charges, than protons. And that's why they become negatively charged. Something like HF, for example, as well. That is a polar bond between the two. And again, because it's diatomic and there's only one bond in there, that molecule also has to be polar. As we'll talk about at the end of this chapter, when you have 3 or more atoms involved, you have to look at some other things when you're doing molecular polarity. But diatomic molecules are pretty simple in terms of polarity. It's basically the same thing as the bond because it's the only bond that's in that particular molecule. Other questions on what we talked about last time? Yeah. So as we saw and as we talked about last time, when we do sort of put together things on opposite sides of the periodic table because of their periodic trends, we have our metals that like to pretty much give away their electrons without a hassle. We have our nonmetals that like to accept them. So again, that's the situation where we are going to create those ions and get a transfer of electrons in our ionic bond. And again, that's different than when we get nonmetals together because they want to both share those electrons or keep their electrons, so we end up getting some type of covalent bond that generally happens. Now, we talked about sort of the numbers and the difference, and we mentioned it last time, and I mentioned, I think, again here today, but again, for the ionic, there are combinations of metals and nonmetals that if you strictly do the difference in electronegativity, you'll get less than 2. So that 2 cutoff for ionic is just sort of an arbitrary one. It works in a lot of cases, but it's not like a super standard case. It's got to be above 2 for it to be ionic. So that's why I said earlier that if you just fall back on metal, non-metals ionic, you're good to go in pretty much all situations. You don't have to worry about it. Sometimes people will refer to bonds in terms of percent ionic character, and 100% ionic character means that you basically have an ionic bond, you have transferring of electrons. 0% ionic character is more of a pure covalent bond where you have perfect equal sharing of electrons. Not too much these days. People refer to bonding in terms of percent ionic character, but it does pop up occasionally. Most of the time we talk about it being polar or non-polar bonds and stuff like that rather than percent ionic character. But that is sort of the difference. So over here, this is obviously an ionic bond. That would be 100% ionic. And over here, we're going to have nice non-bonding non-polar bond, equal sharing of electrons, going to be more 0% ionic, and obviously polar, as we talked about, sort of a middle road between those two. Polar, we don't have a transfer of electron, and we don't have equal sharing of electrons, so we have that unequal sharing of electron. And again, it hasn't got to that point where those electrons jump from one to the next. There is still, again, some aspect of sharing, and that is why we create these partially positive charges and partially negative charges that develop in a polar bond, which can be represented by those delta symbols, or again, that arrow that would point to the more electronegative. So now that we talked about sort of bonding and how electrons are going to be shared, and earlier in this chapter, we talked about how to draw Lewis structures to show ionic bonding. We're going to talk about how you should draw Lewis structures for covalent bonding. And these are really the steps here for our covalent, our sharing of electrons. And if you follow these steps, you really should end up with a pretty good structure at the end of it. If you do it by piecework, which sometimes people do, and what I mean by that is, they'll draw nitrogen and go, it's got like 5 valence electrons, or I'll draw oxygen, it's got like 6, and try to figure out, okay, how they all kind of come together. And when we're dealing with covalent bonding, that's not really a best approach to kind of do that. And what usually will happen if you kind of do that piecework is you'll end up with too many electrons, too many bonds, you know, you won't have the right structure. So more so when we kind of do covalent bonding, we think about the electrons as sort of being trying to spread out and distributed equally among everybody, rather than these electrons belong to this element or these electrons belong to that element. So the really first thing that you want to think about when you're drawing Lewis structures is what is the logical sort of arrangement of how these atoms should be put together. There are some things that can help you. Typically speaking, the central atom is usually the least electronegative atom. So the one that is the least electronegative should usually occupy the center position. I would say a majority of the stuff that we draw in this class, and probably even your next class, will have one central atom and everything else is sort of attached to it. It is possible to have molecules, obviously, to have multiple central atoms and things sort of attached. But probably most of the things that you draw in here and maybe some other classes will be more, there's like one guy in the middle and everybody's sort of attached to it. With that rule being the least electronegative in the center, that means hydrogen shouldn't be there. For main reason of it should only have 2 electrons. So again, if you put it in the center, it's going to have too many electrons. And fluorine shouldn't be in the center either because it is the most electronegative atom that you could have. Probably the most important thing after you sort of figure out how things come together is number 2, and that is the total number of valence electrons in a particular molecule or ion if you're drawing it. That number is really important because when you get that number, you got to hit exactly it on the nose. You can't have any more or any less in your picture. It's got to be exactly that number. That also means that if we have some type of polyatomic ion, which is a group of nonmetals that share electrons but have a charge, you do have to take the charge into account. So as we've talked about, if things have a negative charge, that means that it has gained electrons. So you need to add that to your total. And if something has a positive charge, you then need to subtract that from your total. So for a cation, we subtract actually the positive charge. If it's a cation, positive charge from the total. Again, if you don't do that, you will have obviously the wrong number of electrons when you look at it. Once you have the logical arrangement and once you have how many electrons your picture should have, the first thing you want to do is basically go from the center atom to each of the outside atoms and make one single bond, one bonding bond there. I will use lines personally. Again, you can use dots if you want, but most people will use lines to represent the bonding electrons. Once you do that, a reminder that each line represents 2 electrons, which means if you subtract that off from your total number of valence electrons, you still should have some electrons you need to put on. The remaining electrons will always go from the outside in, which means we want to fill up all the outside atoms as pairs of electrons, so dots, and then work our way in. So we want to fill up all the outside ones as pairs of electrons until each of the outside atoms have 8, except for hydrogen that obviously should have 2 and no dots. And then if you should happen to fill up all the outside atoms and you still have electrons that you need to put on your picture, then you go to the center atom and then you put them on as dots as well. So the goal here is fill up all the outside atoms first. If you still have electrons, you then move to the center and you also put them on as pairs of dots, which are pairs of electrons. At that point, once you start putting dots on the center atom, you should be out of electrons, or you probably did something wrong. So you should definitely be out of electrons at that point. The last thing that you want to do is to make sure that everybody meets the octet rule, which again means that everybody has 8 valence electrons around them. It's at that point, if somebody does not meet the octet rule, then you want to try to fix it. And the way that we try to fix it is to make a double bond, try to exhaust all of our double bond possibilities. And if that still doesn't fix it, then you want to go to a triple bond. You do not want a double bond and triple bond out of the box. It's usually not a good idea. You actually want to save double bonding and triple bonding to sort of fix a situation where somebody does not meet the octet rule. All right, so that's a lot of words. Let's do one here together and see how we put it all into play. So we're going to draw here NF3. So the first thing that we want to do is calculate the total number of valence electrons. Remember that the valence electrons equals the group number. So nitrogen is group number 5, which means it has 5 valence electrons. There are 3 fluorines, and each fluorine is group number 7, which means it has 7 valence electrons. That means when I draw this picture, my grand total of electrons should be 26. Now, in this case, and in most cases, if you just have one element and then other elements, the one element usually finds its way in the middle. So in this case, nitrogen and fluorine, nitrogen is less electronegative than fluorine. So nitrogen should occupy the center spot. We're going to put our fluorines around it. I put the last fluorine on the bottom. You could put it on top. It doesn't matter where you put it. We're going to follow our rules, which is I'm going to do one single covalent bond, not double, not triple. I'm just going to single it up right there. That now has used a grand total of 6 electrons. So if I subtract off from my total, I still have 20 electrons that I need to put on this picture. We're again going to work our way from the outside in. So we will go with pairs of electrons. So 2, 4, 6, 8, 10, 12, 14, 16, and 18. At this point, I have now put on my picture a grand total of 24 electrons. I still actually have 2 more to go. So we can't put any more on the outside. So now that we filled up the outside, we're going to work our way to the center, and we will also put it on as pairs of electrons, and we'll put our 26th electron right about there. At this point, our picture now has 26 electrons. The last thing that we want to make sure is everybody has met the octet rule, and that means that everybody pretty much has 8 electrons around it. So we got 2, 4, 6, 8. So he's good. 2, 4, 6, 8. 2, 4, 6, 8, and our nitrogen 2, 4, 6, and 8. So everybody is good. That would be the proper structure there, minus the highlighting for NF3. Question on that there. So again, we don't want to double bond unless we run into a situation where somebody has not met the octet rule yet. What's that? I thought 6 just is a running count because the first thing I did is put 3 covalent single bonds, and each bond is 2 electrons, right? So that's the 6. And that told me I have 20 more electrons I need to distribute to the outside atoms first. And then if there's any left, like there was in this case, to the center. So you always kind of want to work your way out and then in terms of distributing all the other electrons as dots. Other questions on that? All right. I tried one. You try one now. There, this is the one I just did. Don't try that one. All right. We'll do that. Try maybe this one. All right. NO3 minus, which is nitrate. Draw the Lewis structure for that. See what you come up with. Okay, let's take a look. So we'll start the same way here. We got NO3 minus. So nitrogen is going to be 5. We have 3 oxygens, each are group 6. And here we have a negative charge on that thing, and that means that ultimately it has gained an electron. So we do need to add that to our total, and we will do a +1 here again for the -1 charge. That's going to give us 18, 19, 24 valence electrons. Once again, if we look at the periodic table, we see NOF, which means oxygen is further to the right in that row, which means it's more electronegative. That means here nitrogen should be in the middle because it's the least electronegative. So we're going to do our nitrogen. We're going to put our oxygens. Once again here, we're going to simply just make a single bond between everybody. So 1, 2, and 3. And that again is 6 electrons that I've sort of used for my total. And that will leave me something like 18, I think, to go. And those 18 again are going to be put on the outside as pairs of electrons or dots. So this will be 2, 4, 6, 8, 10, 12, 14, 16, and 18. At this particular point, I have now placed 24 electrons on my atom or my molecule here. And I have no more to put on there. Is everybody good in terms of electrons? Does everybody have 8? The one that does not have 8 is nitrogen, right? So nitrogen actually only has 6 in this case. So this guy is short. All the other oxygens are good. They got 2, 4, 6, and 8, and they're all the same. So everybody's good. Yeah. It does. So that's what the charge means. -1 means it's gained overall 1 electron. Yeah. If it was on -2, you would need to add 2. Yeah. And the same thing if it was a +1, that means it actually lost 1 electron. So you would subtract off from your total of 1. Yeah. Why you do that? Because yeah, ultimately what's happening, even though they're sharing electrons, it has that overall either negative or positive charge, which means sort of overall somewhere along the way, somebody are kind of lost an electron, gained an electron. Otherwise, you would end up with sort of an odd number of electrons, which can happen, but not in our case. But it can happen in that situation. Other questions? All right, so we do need to fix it. So this is the point where we want to fix it. And if I wanted to fix it, I need to make sure everybody has 8. So that is what I want to do. So we'll do a little fixing maybe. Can I just lay up a couple of dots there? I cannot, because now I got how many electrons? 26, which is too many. Yeah, so you can't just add some electrons. So this is a situation where we've distributed all of our electrons. We have not met the octet rule. This is where we roll into double bond action. Yeah, so this is how we're going to try to fix it, is to make a double bond. In this case, I can actually make a double bond at any of the oxygens because they're all equivalent to each other. So I could basically just make a double bond anywhere I like. Can I just lay in there a double bond like that? I cannot, for the same reason. I now have 26 electrons and the oxygen up on top has too many. So when we actually go to make a double bond to fix it, what we're actually going to do is take a pair of electrons, for example, these two, and we're going to bring it in to make that double bond. So those electrons are going to kind of come in to make the double bond. The result of that is I'm going to end up in my example here with a double bonded oxygen up on top. I will still have single bonded oxygens on the sides. And just to make it prettier and stuff, put a little bracket around in the charge on the outside since it is an ion. And now what I have is a structure that still has only 24 total electrons, and everybody is good. My nitrogen now has 2, 4, 6, and 8. The oxygen that's double bonded has 2, 4, 6, and 8. So it's good. And obviously the oxygens on the side are still good with the 8 that they started with. Any questions on making the double bond there? So it's important that when we make the double bond, we actually got to erase the electrons on one of them, bring them in to make that double bond. Now I could have, as I mentioned, double bonded to the left or to the right oxygen. And if I did that, I would end up with a structure that looks like this, for example. And I could have double bonded to the oxygen on the right, which would look like this. And all 3 of these structures are what are referred to as being resonance structures of each other. And resonance structures basically occur when you have an option like this. We had 3 options in this case as to where we could have put that double bond. Maybe you might only have 2 options as to where you could have put the double bond. And the reason for that is those double bond electrons are what are sometimes referred to as being delocalized, which means at any given point in time, they may be over here, but then they may be up here. Maybe they're over here. They're actually moving around. So one Lewis structure doesn't adequately explain the true bonding issue, and it's probably somewhere in between all 3 of those is the correct structure. Yeah, so polyatomic ions, which we'll talk about when we get, are actually non-metals that are held together by sharing of electrons, but because of how they're sharing electrons and who they're sharing electrons with in terms of their electronegativities, they actually overall have a -1 charge in this particular case. So in this particular case, for example, each of these single bonded nitrogens actually have a -1 charge in this configuration. And the double bonded oxygen actually has, that's not right. The double bonded oxygen actually has no charge in this situation. The nitrogen in this arrangement actually takes on a more +1 thing. So when you add all that together, you end up with an overall -1 charge that happens. That's what's referred to as formal charge. We don't talk about it in this class, but when you go to 1A, you'll talk about it. And formal charge tells us sort of what each individual element in a bonding situation where they're sharing electrons based on who they're sharing it with, they take on these sort of different sort of charges. And that's how something like this can share electrons, but still have an overall charge of -1. We also use formal charge, as you'll talk about in the next class as well. You could help you decide between different Lewis structures, which one's like a better structure versus another one based on the charges that you see. Other questions on that? So these are resonance structures. And again, you do not need to draw all the resonance structures unless obviously it tells you or asks you to do so. If you were asked just to draw the Lewis structure, any one of these three guys there would be acceptable to draw. Other questions on that? All right, let's try a few more here just to make sure. Let's do H2S, let's do CH2O, let's do a little N2, let's do SO2, and let us do SO4 2-. All right, so draw proper Lewis structures for all these guys here, see what you come up with. Okay, let's take a look and see how you're working and doing. We'll start with, why not the first one there? We'll do our H2S. So we have 2 × 1 for our hydrogen, plus sulfur's group 6. So that is 8 valence electrons. Obviously, as we talked about, hydrogen cannot be in the middle. It should only have 2 total electrons. So that leaves sulfur to occupy the center spot, hydrogen around. We're going to do a single line to each. That is 4 electrons, leaves us 4 more to go. Will I put dots on the hydrogen? I will not, because you don't want an X. Yes. So remember, that's pretty much done hydrogen. So that means we got to go now to the center atom. And again, we're going to place these electrons as pairs of dots. So 2 and 4. So that is a grand total of 8 electrons. Everybody has 8 in terms of sulfur. And hydrogen has 2, which is what it needs. And everybody's good. Any questions on that one there? Yeah. Yeah, so this is what we were talking about, I think, last time. The goal of all bonding, and covalent bonding is no different, is for them to end up with the same electron configuration as noble gases. And as we look at the periodic table, as we saw last time, hydrogen just needs to get over to helium, which is the noble gas that comes after it. So that's why hydrogen should only have 2 and never more than 2. So if you find yourself putting dots around hydrogen, is probably wrong for sure. Yeah. All right, let's take a look at the next one. We'll go to the right there. We'll do our CH2. So our carbon is group 4. 2 hydrogens, 1 each, and our oxygen is 6. So that's 8, 12 valence electrons. We already know our hydrogen shouldn't be in the middle. When we look at the periodic table, it looks something like this. And we see again that oxygen is actually more electronegative than carbon because it is further to the right. That means carbon actually should be in the center here. Everything else is attached to it. So we'll do a little arrangement like so. We'll do a single bond to each. That is 6 electrons at this point. I got 6 more to go. And as we just talked about, we're not going to put it on hydrogen, but we can put some electrons on the oxygen that's up there. So we'll go with 2, 4, and 6. At this point, I have now placed all 12 electrons on my picture. Is everybody good in terms of the octet rule? I put carbon in the center because usually in the center should be the least electronegative atom. So between carbon and oxygen, which are your only 2 choices to put in the center, because hydrogen can't go there. If we look on the periodic table, oxygen is further to the right, so it will be more electronegative. So that means carbon being least electronegative should be in the center. Yeah. Yeah, you only really want to, again, say double bonding or triple bonding to fix a situation where somebody has not met the octet rule. So basically, you should really distribute all your electrons as dots on the outside, maybe to the middle. And at that point, once you've distributed all your electrons, if somebody doesn't meet the octet rule, that's when you should be looking at double bonding and triple bonding. Once again, you really don't want to double bond or triple bond right out of the box. It's a common urge. People want to do that. It's just like throw up some lines on there on the paper, and you should really try to save it to fix a problem. Yeah. It doesn't. So we stop right in the middle of that conversation. It doesn't. You're right. It only has 6. So we do need to fix it. And at this point, because we've done all of our electrons, we want to fix it by making a double bond. And our only option to make a double bond here is going to be the oxygen. So just like we talked about, we're going to take a pair of electrons and we're going to move it in to make that double bond right there. And we will double bond up our oxygen. We'll keep these guys obviously single bonded. And now when we look at this, we again have a total of 12 electrons. And our carbon now has 8 electrons around it. And our oxygen on top still has 8. The 2 non-bonding electron pairs and the 2 lines for the double bond gives it 8. And everybody's happy in this situation. Questions on that one there? All right. Let us go then to SO4, 2 minus next. So sulfur is 6, oxygen is 4 times 6, which is group 6. And here we will add 2 because it has a -2 charge. So we do need to add those 2 into our total. That's going to give us a lot of math there. That's 24, 30, 32 valence electrons. In this case, once again, if we look at the periodic table, we have oxygen and sulfur. So they are in the same group on the periodic table. Oxygen is further up, which means it should be more electronegative. So in the center here should go sulfur. And we'll put our sulfur in the center. We'll do our oxygens around. We're going to do a single bond to each. That is 2, 4, 6, 8. We appreciate that's 8 electrons there. That leaves us a bunch left, 24. And we're going to put those as pairs of electrons on the outside. So 2, 4, 6. 8, 10, 12, 14, 16, 18, 20, 22, and 24. That's a grand total of 32 electrons. Is everybody good in this arrangement? Everybody is good in this arrangement. And that is what sulfate should look like. Yeah. So like that with a -2 on the end. We'll look at SO2 next, maybe. Maybe I'll do SO2 right about here. Actually, I'll switch page. I got SO2 and N2 left. All right, so starting with SO2, we got 6 plus 2 times 6, which is 12, 18 valence electrons. Once again, here our sulfur should be in the middle, as is the least electronegative. Oxygen's further up. Single bond to each. That gives us 2, 4 electrons. Then again, put the remaining 14 on the outside. So 2, 4, 6, 8, 10, 12. At this point, I got 16 electrons. I still have 2 more to put. And that means I need to go to the center atom and put it as a pair of electrons. That is how those electrons get there. It is not double bonded on both sides, which probably a lot of you have on your paper, maybe right about now. Yes. So you got to make sure you distribute those electrons first. Now, when we look at it, we can see hopefully that sulfur is actually short, right? Sulfur only has 6 electrons and the oxygens are okay. They all both have 8. So here we can make a double bond to fix it. And we can do either oxygen, right, as they're both equal to each other. So we're going to take a pair of electrons, say from this oxygen, and bring it in to do so. And we will end up with something that looks like this. And this is also another one that we could draw a resonance structure for, where we could have double bonded to the left there. And now the sulfur in the middle has got 2, 4, 6, 8 electrons. Each of the oxygens have 8 as well, and that would be the correct picture. Yes. Yeah, typically when you put them on, they should come on as pairs of electrons is how you want to place them, so they should be together. Yeah. Other questions? Okay. And lastly, here we have nitrogen, which is N2. Which would be 2 times 5, which is 10 valence electrons. In this case, there really is no center atom, so just going to kind of place them next to each other. And you really could still follow the same procedure. We could connect with a single bond, which is 2 electrons. We got 8 more to go, so 2, 4, 6, and 8. We can now see that we place all 10 electrons, and hopefully you can see the nitrogen on the left is quite short. It's only got 4 electrons. So we could try to fix it by making a double bond. It works the same way. We'll take the electrons and move them in. And when we do so, we will end up with something that looks like this. Did that fix the deal here? It did not. So it got better. He's 6 now, right? He needs 2 more. So in this case, we have no other option for double bonding. Now we want to move to triple bonding. So we're going to do the same thing. We need to bring another pair of electrons in to make the triple bond. So we'll take a pair of electrons in to do so. And this is how nitrogen ends up with a triple bond in the middle there. Any questions on that? Now each nitrogen has 8. Yeah. You don't. I'm just showing it so you can see where it all comes from. I would hope to see something rather than just randomly it just popped out. I know the triple bond type of thing. So just, maybe there should be a little bit of that, but I'm just showing you step by step how it kind of comes in there. Any questions on that? Questions on how to draw Lewis structures. If you follow these steps, you should end up, like I said, with a pretty good picture at the end there. Probably the right picture. Yeah. This is all about covalent bonding. Obviously, we did it for ionic bonding, and that's where we left charges in, right, and transfer of electrons. But for covalent bonding, these are the steps that you should follow for a covalent type situation. Now, we did talk about that in a lot of cases, there will be 1 central atom, but there could be something where there's 2 central atoms. And for example, here, we looked at something like nitric acid, which is HNO3. It has 1 for the hydrogen, 5 for the nitrogen, and 3 times 6 for the oxygen, which is 18, 19, 24 valence electrons. Now, this is going to be arranged very similar to nitrate, but actually what makes it an acid is, in this case, the hydrogen is actually connected to the oxygen. And in a situation like this, if you didn't know it, I would tell you how it's sort of arranged, but we do have sort of our least electronegative atom, nitrogen, in the center, and our next sort of oxygen next to it. It still works the same way, regardless of the 2 central atoms, which would be nitrogen and oxygen in this case. You do just make 1 bond to everybody. And in this case, we have used now 2, 4, 6, 8 electrons. We got 16 more to go. We will still work outside in, so we will not put anything on the hydrogen, but we can put some on the oxygens on the outside. So 2, 4, 6, 8, 10, 12. At this point, I have used 2, 4, 6, 8, 10, 12, 14, 16, 18, 20 electrons. I still have 4 more to go. The next outside atom is actually the oxygen on the right, and we can put those 4 electrons there. At this point, we've now put all 24 electrons. Is everybody good in this situation? The nitrogen is short, right? The nitrogen actually only has 6 electrons. So it's only got 2, 4, and 6. So here again, we would make a double bond. And in this case, you could do it from the oxygen here. You could do it from the oxygen here. Most likely, you wouldn't do it from the oxygen here because that's actually what makes it an acid, that OH bond. So you probably wouldn't play too much with that one. But for example, we can take a pair of electrons in to do so, and you will end up with something that looks like this. And you can see, you can still follow the same steps, even if you have multiple central atoms, it all works the same way. You could also, again, draw a resonance structure for this where you maybe double bonded up over here. As well. Any questions on how to draw a Lewis structure? Yeah. It probably wouldn't, for a couple of reasons outside of this class, but really what makes something an acid is the ability to lose that H, and that's what's going to really pop off. Technically speaking, you could lay up a double bond there, but probably the other 2 would be more suitable for that. It won't play with the polarity of that and allow that hydrogen basically to come off. Yeah, so this is again possible, a couple of different arrangements. You might not be able to put the hydrogen in the middle and still be able to get everybody to the octet rule. So for example, in this one, if you try to lay up the hydrogen in the middle there with everybody else there, you still be short electrons somewhere. And so it won't work that way, and that's because it has to be that way. But that's a place where it is possible to come up with different sort of Lewis structures, for example. But you can use something like formal charge to help you decide which one's the better one if you can draw a Lewis structure. But for our purposes, in most cases, everything will be attached to the one central atom, but it can obviously have multiple central atoms, and you can still follow the same rules to draw them. Other questions on Lewis structure? Yeah. This is bonding. So nomenclature is naming all these things. Yeah. Lone pairs are the non-bonding electrons, or the electrons not involved in a bond. So they were represented in these pictures as the dots. And the bonding electrons are represented as the lines, obviously, because they're between two atoms. Yeah. Other questions? Yeah. All right. Let's continue talking. This is carbonate, which is very similar to nitrate. So I'll just scroll it up here, and that's sort of what you end up with as well, a double bond needed. So let's talk a little bit about bond length. And bond length, you do not have to memorize this table, but if we look at the relationship between a single bond, double bond, and a triple bond in terms of a carbon-carbon, the single bond is 154, double is 133, and 120, the distance between the two atoms. And if we look at the carbon nitrogen, single, double, and triple, we see a similar pattern, 143, 138, and 116. What we see here is every time we bring those electrons in to make one more bond, we put more electrons between the two atoms, brings everybody closer together. When we make a triple bond, everybody gets moved closer together. Again, you have a lot more electron density in the middle between the atoms, going to attract the nucleuses, which are positively charged, and it's going to bring everybody closer together. So every time you put a bond on, the distance between the two atoms gets smaller, and that affects the bond strength that we see. A triple bond is stronger than a double bond, and a double bond is stronger than a single bond. It's not like a triple bond is 3 times as strong as a single bond or anything like that, but that is a general trend. And again, a single bond is the longest of the bonds, followed by a double bond, and the shortest would be a triple bond as everybody moves together. I think of it like a pencil. Get a brand new pencil like out of the box, right? You could take it and snap it, no problem, right? It's nice and long. You take a chemistry test, you got like an eraser and a nubbin of a pencil left, right? It's like super hard to try to break that, right? Everything's all condensed together, and that's what happens as everybody moves closer together, and all those electrons bring the nucleuses and everybody closer together. Much more energy is required to break a bond like that. Any questions on that there? Now, resonance structures, we sort of touched upon there as we were drawing our Lewis structures, but resonance structures really do arise in a situation, as we talked about, where you do have, a couple of options as to where you could lay up that double bond. And again, we could draw multiple structures to sort of help us show where those double bond electrons could end up. And they're all sort of equivalent structures to one another. So some of the examples there is like our ozone, for example. If we drew ozone and went through our journey there of drawing the Lewis structure, we'll end up with some structures like this. And we could double bond here to the left, and we could also double bond to the right. The charges that you see on here are the formal charges in ozone. So in this case, the oxygen in the middle is carrying a +1 charge. The oxygen on the right there is a -1 charge, and the oxygen on the left has no charge, which gives ozone neutral overall, as all those charges cancel each other out. But again, those are two resonance structures. We do use this arrow to sort of separate resonance structures. So if you see that arrow between two structures, that's basically two resonance structures of each other. Here is carbonate, which again, those are the formal charges in carbonate. The -2 that carbonate has actually is on the single bonded oxygen, is actually where the charge comes from. And those are 3 separate structures for carbonate. Each one is perfectly fine if you were just asked to draw a structure of carbonate. For our purposes, you don't have to include the individual charges. You could just put a bracket around it with the -2 on the outside. But that's actually where the -2 sort of ends up. Benzene is something that you might come across in organic chemistry. It's a 6-carbon molecule that has 3 double bonds. Everywhere there's a point, it's actually a carbon. And it can also resonance structure where those double bonds are on opposite sides. And sometimes you'll even see benzene drawn with a little circle in the middle, and that indicates that those double bond electrons can kind of move around from each carbon to each carbon in there. But it does have 3 actual double bonds. Probably won't see it too much until you get to organic again, and then you'll never see anything but that. All right, so that is resonance structures. Here's just another example of some different resonance structures that you could draw, where you got multiple double bonds happening. So you can see you could draw equivalent structures just kind of moving around those double bonds to different locations. Now, we talked about the octet rule, which very clearly means that everybody will continue to make bonds until it has 8 electrons around it. And for our class, for sure, everything that you draw should obey the octet rule. But there are exceptions to the octet rule, so you'll save those exceptions for when you go to 1A, where you do nothing but probably draw things that are exceptions to the octet rule. So for here, we will obey the octet rule, but you do need to know the exceptions. So one exception to the octet rule is there are certain things that can have what is referred to as an incomplete octet, which means they're perfectly happy with less than 8 around them. The most common one that you probably come across most of the time in your chemistry career there is boron, and boron is electron deficient and is perfectly fine with 6 electrons around it. It doesn't need 8. Beryllium and aluminum is also included in that list, but most of the time covalently bonded boron is really the guy that kind of shows up most of the time. If you look on the periodic table, we got beryllium, boron, and then down to aluminum are the ones that can sort of do that incomplete octet. But again, boron is probably most often what you would see in that case. Another exception to the octet rule is an odd number of electrons. And NO and NO2 are examples of that. An odd number of electron would mean that you will end up with 1 unpaired electron, which is also why an earlier question, you do want to pair up your dots and not put them as single dots, because it could imply that it is an odd number of electrons and that you have like a free radical, they're sometimes referred to. Free radicals are things with 1 unpaired electron, like in chlorine chemistry in the atmosphere. They are very reactive because they have 1 unpaired electron. They don't really want to be that way. They want to kind of fix that situation. So they're very, very reactive type things. Now, obviously, you would get that when you would add up your total number of valence electrons. You end up with an odd number. Again, for our class, if you do that and you get an odd number, it's probably wrong, because you should obey the octet rule. You probably should end up with an even number when you do it. The last exception to the octet rule is one that you will see the most in probably your chemistry life, and especially you will see it the most when you go to 1A, and that is the expanded octet. And there are certain elements that can go above 8 electrons. They could go upwards of 12 electrons, which is 6, kind of bonds that could happen, or 6 pairs of electrons around it. And on the periodic table, if you look at where sulfur is, and you go to the right, you go to the left, and you go down where the nonmetals are, those are the guys that have the ability to go above 8 and do the expanded octet. And that is because sulfur is on period number 3 of the periodic table, which means that is the 3rd energy level. And on the 3rd energy level, that is where we actually see s orbitals, p orbitals, and that is where the first set of d orbitals, where electrons are housed in an atom, actually happen. So because they have the d orbitals, these extra sort of places to put electrons, they have a place to stash all those extra electrons, and they're able to go above 8. That's also why when you look at the periodic table, nitrogen, oxygen, fluorine, that is the 2nd energy level. And on the 2nd energy level, there's only s orbitals and p orbitals. They do not have d orbitals, which means those guys should never go over 8. So it has to be sulfur left, right, and down. When nonmetals, it could go over 8. Again, when you get to 1A, not when you do it here. We should obey the octet rule. And this is also why, for example, if you drew something like sulfate that we just looked at, you'll end up with something like this. But perhaps if you Googled sulfate because you just wanted the answer, which I'm sure nobody would ever do, you might see a structure that looks something like this with some double bond action happening there. That sulfur there has 2, 4, 6, 8, 10, 12 electrons. And that also is sulfate. That's an expanded octet, and sulfur can do that because it can go over 8. Clearly, you shouldn't do that in this class because they know you Googled it, because we don't do over 8 in this class, and you wrote the wrong structure down, right? So make sure you draw this stuff yourself later on and you get the right structure. I will tell you the truthful answer is, based on what we were talking about, formal charge, that's actually the better structure, the one with the double bond, but following the octet rule should get you to the guy on the left. So you definitely should do the guy on the left. SF6 is an example of that, and it works the same way. You will end up with basically, and I won't draw all the dots on the fluorines, but they all have their non-bonding electrons. This sulfur, 2, 4, 6, 8, 10, and 12 electrons around it. So for us, always obey the octet rule, but you do need to know just what the 3 exceptions are. Incomplete octet, less than 8, odd number electrons, odd number one non-paired up electron, and expanded octet over 8. Any questions on that there? All right, so now we're going to talk about geometry here and molecular geometry. And we're going to talk about two types of geometries. This is going to be the electron pair geometry. And for the rest of the time here, I'm just going to call that the EG. And we're going to talk about the molecular geometry, which is sometimes referred to as the shape. And I'm going to, for this purposes, call it MG. So EG and MG will refer to electron pair geometry and molecular geometry. These are two names to describe the arrangement of, in the case of electron pair geometry, the electrons around the central atom, and the molecular geometry, the actual overall shape of the molecule. When we do molecular geometry, it is all about the central atom. CA, yeah. So you always want to, when you look at it to do geometry, always want to focus on the guy in the middle, the center atom. That is the most important thing. So let's talk about how we can do this. When we draw Lewis structures, we can use what we see in terms of the central atom to help us decide what geometries there are. And I would say most people can't visually see 3-dimensional things in their head, myself included. So really the best way to know these is just to memorize the electron pairs and the bonds and what geometries go with it. So there's really 2 things that we look for when we do look at the central atom. We want to know the number of electron pairs around it, and we also want to know the number of bonds. So those are really the 2 things that you want to look at. And based on the number of electron pairs or the number of bonds that are present, it will give you a certain geometry for that particular molecule. The basis of this approach is, frankly, bonding involves electrons. Electrons are negatively charged. So what happens when people make bonds? Negatively charged electrons get near negatively charged electrons. Do 2 negatively charged things want to be near each other? They don't. So the whole purpose of geometry is, frankly, what happens, they move around to try to get as far away as possible from one another. But in certain cases, they can't escape because they're locked into a bond. But what will happen is they will move. And as they move those electron pairs, anything that's bonded will move. And what will happen is the overall geometry of the molecule, or the shape of the molecule, will kind of change accordingly depending on what electrons are present. This is what's known as VSEPR, which is the valence shell electron pair repulsion model, which is why the abbreviation is there. That's a mouthful. And it's basically divided into 2 categories. When we draw our Lewis structure, we have center atoms that do not have lone pairs, are non-bonding electrons. So basically, if you draw your Lewis structure, you have no dots on the central atom. And we have ones that do have lone pairs, which means when you draw your Lewis structure, you got some dots happening there on the central atom. One of the most important things when we do geometry, and only when we do geometry, is we treat any double bond or triple bond that you have in your picture. It counts as only 1 electron pair. are one bond. So double bond or triple bond count as one electron pair and one bond. So even though they're double bonded or triple bonded, they're effectively working as one sort of unit, and we count them as only one, and that's really important. The second thing is also important, but not so much, but we talked about drawing resonance structures. You could actually do geometry to any resonance structure that you draw, and in most cases, there'll be the same sort of geometry for every resonance structure that you draw. All right, so let's talk about how we kind of do this. So as we go through, we're going to talk about both of those names, electron pair geometry name and the molecular geometry name. And we're going to talk about the number of electron pairs and bonds. But first, we're going to talk about really the simplest one that you could have. And you don't have to worry about all the numbers and letters and stuff like that. But really the simplest geometry that you can assign is anything that's a diatomic molecule. And that basically just means there's two things, right? So if you have something like H2, you have something like F2, you have something like HF, you have oxygen, which has a double bond, you have nitrogen, which has a triple bond. All of those guys are diatomic molecules. And when you only have two atoms, or where you only have two things, simplest way to connect two things is a straight line, right? So the only way you could arrange two things is a straight line. And all these geometries, regardless of which one you're looking at, they will all be linear. So whenever you see a diatomic molecule and you want or ask what the geometry of it is, just write linear. And again, it doesn't matter if it's single bonded, it doesn't matter if it's double bonded, triple bonded, doesn't matter if it's two of the same or two different. They will always be arranged basically straight line of each other in a linear fashion. Any questions on that there? When we have three or more atoms in a molecule, we have to look at the center atom, because obviously in the two situation here, there is no center atom, right? There's just two atoms. So when we have three or more atoms involved, you always want to look at the central atom, and that's where you want to pick out the number of electron pairs and the number of bonds. So let's take a look at it here. We'll take a look at our first example. This is an incomplete octet. And if we look at the central atom here, the number of electron pairs is 2 in this case, 1 and 2. The number of bonds is also 2, 1 and 2 in this case. The electron pair geometry is based on the number of electron pairs. So something with 2 electron pairs is linear. The molecular geometry in this case is also going to be linear, or the shape of it. And that is because these bonded atoms pretty much want to get away from each other. So they go on opposite ends of each other. And they end up being 180 degrees apart from each other in terms of our bond angle here. And that would be linear. Both the electron pair geometry and the molecular geometry are the same name. And that's because it is bonding electrons. So as those electrons move, so does the bonded atoms, right? So as they move together. So the shape and the electron pair geometry are going to be the same. Any questions on that one there? The next example that you guys have is a central atom with sort of 3 things attached. And if we look at our central atom, which is always where you want to look, it has 1, 2, and 3 electron pairs. It has 1, 2, and 3 bonds as well. So something with 3 electron pairs, the electron pair geometry name is trigonal planar, and it's sometimes referred to as triangular. The molecular geometry name, again, because those are all bonding electrons, those atoms will move the exact same way, and that is going to be trigonal planar as well. It has a bond angle of 120 degrees. It's also called triangular because, frankly, it makes a pretty triangle, yeah? So it makes basically an equilateral triangle, and that's why it's sometimes referred to as triangular. Once again here, both the electron pair geometry and molecular geometry name are the same because they're all bonded atoms. So as those electron pairs move, the atoms go along for the ride, so they end up in the same location as where the electrons do. Yeah. All right, the next situation that you could have is a central atom where we got 4 things attached. And again, if we look at the central atom, number of electron pairs is going to be 4. 1, 2, 3, and 4. The number of bonds will also be 1, 2, 3, and 4. So something with 4 electron pairs, electron pair geometry is what is known as tetrahedral. Once again, these are bonded electrons. So as those electrons move, the atoms that they're bonded to, like the hydrogens, move with them. And it ends up with the same molecular geometry, which is tetrahedral as well. It has a bond angle of 109.5. Kind of makes a triangle on the face, a little pyramidal sort of action happening there on the bottom. Yeah. They want you to know those things. So you do need to know the bond angle and both of these names that we're talking about here. Yeah. Other questions? So up until this point, as we see, both the electron pair geometry and the molecular geometry name are going to be the same. And again, that always happens when you have no dots on the central atom. And that's because all of those electrons are bonding electrons. So as I mentioned, as the electrons move, so does the bonded atoms move with it. So everything ends up being the same. So whenever you draw a Lewis structure, no dots on the central atom, both of those names will always be the same name because the geometry will be the same for them. When we start introducing non-bonding electrons on the central atom, dots on the central atom, we start to get different molecular geometry. So this name starts to change. The electron pair geometry will remain the same, but the molecular geometry will change because there's not an extra atom there with those non-bonding electrons. And the non-bonding electrons and bonding electrons really don't like to be near each other, so they try to get further away. So when we look at the 3 types of interactions that could occur with electrons in a bond, the best situation is bonding electrons near bonding, so kind of lines near lines in your Lewis structure. The next sort of worst situation is non-bonding electrons near bonding, so dots near lines. And the worst situation that could happen is where you get non-bonding electrons near non-bonding electrons. Those guys want to get as far away as possible from each other. So as they are trying to escape each other, anything that's bonded starts to move. And that's why we see the overall molecular geometry names start to change because of that. And let's take a look at an example of that. So the first example will be sulfur dioxide that we drew earlier. And if we look at sulfur dioxide, it looks something like this. And I'm just going to draw the electrons on the central atom. Oxygens have it. The number of electron pairs here is 1 electron pair, 2 electron pairs, and our double bond counts as only 1. So that is 3 electron pairs. The number of bonds is 1 bond here, double bond counts as only 1. So this guy would have only 2 bonds. So again, double bonds, triple bonds counts as 1 electron pair and 1 bond. Something with 3 electron pairs, as we saw earlier, the electron pair geometry name is trigonal planar. But now because we have these non-bonding electrons, they're going to try to get away those oxygens away from it as far as possible, but they also got to keep a little distance from each other as well. So what ends up happening is the molecular geometry name is, I'm going to go with angular. Some people will use bent for this one as well, or some people will use bent angular. The bond angle here is less than 120 degrees. So it's a little less, and it's because it doesn't have that extra third bond. It's got those non-bonding electrons. It's able to kind of move a little bit more, and we start to see a change in the molecular geometry name. Any questions on that there? Yeah.
So that's if it has a lone pair? That's if it has 3 electron pairs and 2 bonds and 1 lone pair on the central atom. Is that what you're asking? Yeah. Other questions? All right, we have 2 more geometries to talk about, so let's talk about them here and to wrap it up here. The next example is ammonia. And we look at ammonia here and we look at the central atom. Our central atom, number of electron pairs, it doesn't matter if they're lines, doesn't matter if they're dots, doesn't matter if they're single bonded, double bonded. That is 4 electron pairs. It has 1, 2, and 3 bonds. So something with 4 electron pairs, as we saw earlier, the electron pair geometry is tetrahedral. And now what happens is, again, we have the non-bonding electrons, and those bonding electrons are going to try to get away from each other. But again, these guys also need to kind of keep their space from each other. And we're going to end up with a molecular geometry known as trigonal pyramid. And that is because it makes a triangle and now a pyramid type shape there on the bottom of it. And it has a bond angle of less than 109.5 degrees. So let's talk about this name. That is trigonal pyramid. Earlier, we also saw trigonal planar. They are different. So on a test or quiz, do not just write trigonal, because you will get an X if you make me choose, because I failed this class. Yes, so don't do that. Also, don't do my other favorite, which is trigonal as planar, pyramid. I'm not really sure, right? So make sure you choose wisely on that particular one. Any questions on that one there? Lastly, here in terms of the geometry that you're responsible for is water. I'm not sure where it went on my slides, but maybe you have it on yours. So if we look at something like water, for example, we have a central atom that has 4 electron pairs, and that is 1, 2, 3, and 4. Number of bonds is 1 and 2. So something with 4 electron pairs, electron geometry name is going to still be tetrahedral. But in the case of water, we actually have the worst situation happening. We have non-bonding electrons near non-bonding, bonding near non-bonding, and all 3 interactions. So what happens is these non-bonding electrons try to get away from each other, causing these guys to come down. And once again, they can't get too close to each other as they're moving down away from each other. And we end up with a molecular geometry known as bent or V-shaped, which is why we're going to use angular for the other one. And it has a bond angle of less than 109.5 degrees, about 104 degrees is what water is. And that is the geometry that we see here for 4 electron pairs and 2 bonds. The best thing to do is to make a table, and I actually made a table for you as well in exam 2. There's a thing that says like geometry and polarity. If you click on that, it will give you all this table and stuff like that. There's also a table in your book that looks similar to this. You are responsible for the electron pair name, the molecular name, and the bond angle for these. But that really is the best way to memorize these sort of geometries, is go number of electron pairs, number of bonds, and what geometries it relates to. Yeah. It's always linear. Yeah. So that's the safe bet. 2 things bonded. Again, 2 the same, 2 different, double, triple bond, always going to be linear. Yeah. This table is in your book. I made a separate one about geometry and then also polarity, molecular polarity. So if you look under exam 2, there's a little thing that says like geometry, I think, and polarity.